Okay, let's start. Okay. So this is lecture number 1, and today we are going to look at some basics related to matrix and vectors, and also about some special metrics that exist. Okay. Okay. So the topics today is going to be matrix and vectors, matrices and vectors, and also some issues related to some special property related to this. Okay, so let's start. So first of all, when we talk about matrix and vectors, what's the main difference? Okay, if we talk about 1D, then we call it vectors. Okay, and formally, they are formally, when we say vectors, we generally define it as a column vectors. Okay. So in this type of vector, it's different from in physics. In the case that there's no direction, we just have the components inside the vectors. Okay. You can think about it as the vectors in terms of physics as well, but in here, there's no direction per se. Okay. So for example, if I define a vector, and by definition, it's a column vector. Okay. It means that the values in this vector spans in the column, direction. So let's say this is a vectors called with the element 1, 3. Okay. So this is called column vectors. It has 2 rows and it has 1 column. Okay. And sometimes we write the dimension or the size as number of rows multiplied number of column. Okay. So here we can call it the size, or some people call it dimension, this is informal name because the word dimension can also mean differently, And if you want to make a row vector out of this, so we have to do a transpose. Okay. So I guess some of you have learned about matrix and all this before, right? So if you do a transpose, what do you get in this case? Thanat, what do we get in this case?
We get 1 row and 2 columns.
Yes, so we get 1 and 3, right? Therefore, we switch between number of rows and number of column as above. So now we have 1 by 2. Okay. So whenever you look at any work, any research work or any project, and when you write program in either MATLAB or in Python, you always will always designate a vector as a column vectors like this, always, no? So that we don't get confused later when we talk to other people or when we write the code and we try to see, whether, when there's some very long expression that it has a lot of vectors and matrices that connect together, then everyone, talk on the same language or the same definition of vectors, the dimension, Okay. So that's first of all. Okay. So next, let's talk about some basic stuff like addition. Okay. You can operate you can have some operation on vectors and matrices. Okay. For example, if you have x is equal to value, say x1, x2, x3, x4, and we give the y vector. Notice that when I write it down here, if you write on your report or you write on your conference paper or journal, you always make it like a bold face. But when we write like on sheets or write with the handwriting, we always put this the underline instead. Okay, so if you print it or you type it, when during typing or printing, by IEEE standard, we will use the bold face so that we separate between variable and vectors. Okay, so this will be like variable. So this will be a vector or a matrix. Okay, we always do that. Okay, so in this case, let y equal to let's say it's a 4 by 1 dimension of 4 by 1. Okay, and this is second one. So in this case, when we say x plus y, okay, what do? We just do an addition by element. Okay, and then 4. Okay, you can have a larger dimension than this is okay. 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 And if you look in terms of vectors, sometimes we can draw the addition like this. Let's say that, let me change color slightly. Let's do it orange. Let's say that if I have x here I put x with a bold face, okay? And then let me have like a y. Let's say y is here, okay? So if I try to sum up together, if I have x plus y, I can just draw x and then followed by y like this, okay? And the results, if I use the red colors as the results of x plus y, then I will get something like this, okay? This is when you put the direction together. But generally, yes, you can do it or you don't do it, okay? Similarly, if you multiply x with the some constant value, let's say it's 2x, so this will be, it will have the same direction as x, but it has the twice as long, the side becomes twice, okay? So this is like I would say like a typical vectors, that you learn in engineering or physics, and all that. Okay. So if previously we have x as the dimension of 4 by 1, okay. Let's say I have infinite dimension, like infinity by 1. Do you know what's the name that they call if you have like a infinite dimension of matrix? I don't know if you've heard of it, but it's called Hilbert. We talk about Hilbert spaces. Okay. So this is when you have infinite dimension. Okay, so that's it. Okay. Next is multiplication. This one you've seen it before. So very basic, no? If it's very basic, so don't worry. It will become much faster later. Okay. So when we have like a multiplication, if let's say x is a vector with 3 by 1 dimension like this, Okay. We can multiply with the vectors itself, or we can multiply with the constant value. So if I have like a c multiplied by x, so what do we have? We just have cx1, cx2, cx3, cx4, and etc. Okay. For example, if I have x equal to, let's say, 1, 2, 3, okay, and I want to find 2x, okay, what do I get? Tanat answered earlier, right? How about other people? How about Pio? What do we get here, Pio? I cannot see the chat screen because I leave it on. How about other persons can answer this?
2, 4, and 6.
2, 4, and 6. Okay, that's fine. Okay. Next, let's look at another operation. This is called inner product. Okay. So we will hear this term, come up quite often about what is it called inner product. In essence, what is inner product? Inner product is when we try to map from vectors or matrices into real number. Okay. So that's what happened. And okay, so let's say that, and this real number has one dimension. Okay. So what is inner product? Inner product comes into various form. For example, let's say I have A as a vector, says A1, A2, A3, A4. Okay. And then I have B, which is also another vector. Let me write it as B1, B2, B3, and B4. Okay. So when we say inner product, the very formal definition, formal notation of the inner product is like this. Okay. So we just put this bracket, on two sides and then comma between A and B. Okay. So this is a very formal notation. Okay. But sometimes when we hear a special case, which is dot product, okay. Oh, I can say it this way, that for formal definition of the inner product, it can be defined many ways. Many ways. Okay. For example, one of which is the dot product. Okay. And in this case, we can write it as like A dot B, for example. That's one way of writing at it. So for this special case of the dot of the inner product, which is called dot product, then in this case we can write that A dot B. Like I mentioned earlier, when we say A dot B, this is to convert the vectors into real number. Okay. And one of the definition is A transpose dot B. Okay. Or if we write down A transpose, we get A1, A2, A3, A4. And for B, we have B1, B2, B3, and B4. Okay. And so what do we get here? Okay. Can you multiply? Is Pure here now? Pure? Mhm. let me try to log into the Google Meet with another tablet, no, so I can see you guys and I can talk easier. Okay. Okay. So how about Tanason? Have you
Okay.
answered yet? Have you answered
Yeah.
already? You answered already, right? One time.
Okay.
How about Tirawit? Is Tirawit here? Tirawit.
Yeah.
Oh, okay. Here, what do we get here? If you multiply this row vector with the column vector, when we multiply between how do you call it? First of all, let's look at the dimension. Okay, what is the dimension here, Tirawit? For A, what is the dimension?
1/4.
Yeah, it's 1 multiplied by 4. How about the B? What is the this B? What is the dimension?
4/1.
4 by 1. Yes. So when we multiply it, we will get the size of
1/1.
1 by 1. Yes, exactly. And in order to multiply, there are different ways of multiplication depending on how you want to save time. But a very simple method is let me change color, no? Here, red color. We multiply each row, the element in each row with the elements in each column. Okay? 1 by 1. Okay? And last one is A4 and B4. So what we get here is A1, B1 plus A2, B2 plus A3, B3 plus A4, B4. Okay. So in general, we can write this as summation of AI, BI, I equals to 1 all the way to N. Let's say in this case, N is equal to 4. Okay. So this is the dot product. And let me put like this, multiply A transpose and then A dot product. Okay. So we can write it like this. Okay. So that means that whenever we see this type of summation, and n can be large. Let's say if you have n equals to 100, you have a very long summation. It keeps adding, adding, and adding. So instead of writing like this, you can write it like this as a summation instead. Or even better, when we process in computer, we can write it like this, which means the same thing. Okay. Okay, so let's take a look at an example of this very simple dot product. Okay, so let's look at an example. Okay, let's say we let A equals to some vector. Okay, so can anyone give me some number just for fun? Okay, how about Tanat?
Okay.
Yeah.
2, 3, 4.
Okay, 2, 3, 4. Okay, so you do 3 by 1, right? How about B? Thanatson, can you give some values here?
6, 7, 3.
5, 7, 3, right? Okay. How about Thirawit, can you multiply A transpose multiply with B? What do you get? What is A transpose?
2, 3, 4.
2, 3, 4. How about B? Is 5, 7, 3, right? Okay. So what do we get as a result?
43.
Okay, so it's 2 multiplied with 5, 3 multiplied with 7, and then 4 multiplied with 3, right? Okay, which is what?
10.
10 plus
21.
21 plus
12.
12. Okay, so we get what? 43.
3.
Oh, 43, right? Okay, that's it. Okay, so these are some very simple way of operation with vectors, you know. Also, if we do A plus B, this will be equal to B plus A. Okay, some property. If we do A minus B, this is the same as A plus minus B. Okay, so yeah, so that's about it. Okay, next, let's look at what we call matrix or matrices. Okay, so in singular, this is matrix, right? Matrix is just two-dimensional vectors, okay, or more. You can have more dimension as well, or more dimension, okay. If you have a lot of matrix, we call matrices, M-R-I-C-E-S, matrices, okay. So what are the matrices? So matrices for the 2D version, you know, it's just like a we call ordered array with m rows and n columns. Okay. For example, if I let A is equal to our matrix with m equal to 2, n is equal to 3. So we have 2 rows and 3 columns. Okay. Let's say just you know, some numbers just for fun. 2, 4, 2. Okay. So in this case, we have 2 rows multiplied with number of columns, which is 3. Okay. Okay. So if you have like many samples of data, let's say you have like 1,000 samples of data, and you have to convert them into matrices, you can do many ways of putting into matrices, you know. You can do in terms of vector 1000 multiplied by 1, okay. You can do in terms of matrices 200 multiplied by 5, you know, and so on, okay. And so there are also some special metrics that we will run into quite often. Special metrics. I'm sure you know some of these already. Okay. For example, number 1, we can look at square matrix. Okay. 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 Thanat, what is a square matrix?
A matrix has a row and equal row and columns.
Yeah, the number of rows and columns, you know, are equal. So in this case, m is equal to n, basically, right? So for example, if I give like a B is equal to a square matrix of 2 by 2, okay, then maybe I write, I don't know, 0, 1, 3, 5, for example, you know, with the 2 rows and 2 columns. Okay. So that's one. Okay. Next one is we called identity matrix. Identity matrix. Okay. So this one we have first of all is a square matrix as well, but the values in here, let's and say m equal to n. Okay. So In is defined as a matrix with m rows and m column. In this case, I say n, no? So it's n rows and n column. And for this matrix, you have one at the diagonal position. Okay. So we have some numbers like these. Okay. And all the way to like this. Okay. So when we say diagonal position, we mean, you know, this this position. Okay. So when we say diagonal position, we mean that okay. So when we say diagonal position, we mean the if this is equal to Aij, okay, at the j row and the I row and the j column, okay. Diagonal position means the position where I equal to j, okay, which is 1, 1, 2, 2, 3, 3, and all the way to n, okay. So that's a second special matrix. Okay, next one is a null matrix. Can you guess what a null matrix is? Some people just call zero matrix. Okay. So a null matrix is the matrix where all elements or all the values are zeros. Okay. So that's all. For example, we can have the notation is normally 0 and then n by n. Okay. For example, you can have all 0. Okay. I don't know, just all 0, you know, just write like this. Can null matrix, you know, do they always have to be square matrix for the null matrix? So in this case, it's a square matrix. Okay. Yeah. Does a null matrix need to be square matrix always? Not really, you know. It can be m by n. For example, if I talk about a null matrix of the size 2 by 3, what do we have? We have 2 rows and 3 columns, you know, like this. Okay. Okay. So I mean, these are some metrics. Okay. I talked about the identity matrix, and let me also write down some properties of identity matrix. Okay. So let's given an X matrix. So if I multiply X to identity, let's say the if I multiply the matrix X multiply with identity matrix of dimension n by n, okay, what I will guess is I will always get the X matrix, okay. And similarly, it's equal to identity matrix multiply with X, okay. Okay. Next, let's take a look at some other special metrics. Okay. Let me see. Maybe there's more on here. Related to multiplication. Related to multiplication earlier. Okay. Theorem. When you multiply matrix, A multiply B multiply C, okay, you can do arrangement, you can do grouping, you know. You multiply from left to right, and you can multiply from any pair first, and you get the same results, okay. Related to the multiplication, another thing is multiplication is not commutative, meaning that this is different from A plus B, but from A multiply B is not equal to B multiply A. Okay. We call non-commutative. Okay. For example, if you take a look at some, let's say it's 2 by 2, no? Just for simplicity. If I give A equals to, let me see, who should I call? Is Pure back yet? Pure, are you back?
Yes.
Okay, give me some numbers for the 2 by 2 matrix.
5, 7,
Okay,
6,
okay,
3.
3, okay. And let me look at B, okay. B, okay. Can anyone give me another matrix? How about the who don't I call often? Thanatson. Okay, Thanatson. Give me another B.
Okay.
Okay.
10,
Oh, don't give too many number. Too large number.
9,
9. Okay.
1, 2.
1 and 2, right? Okay. So let's multiply A times B. Okay. So what do we get? So I write like this: 5, 7, 6, 3. Okay. And multiply with 10, 9, 1, 2. Okay. So given the matrices from pure and from Thanatson, right? Okay, maybe Thanat can help me multiply this one.
Sure.
Okay. So what do we get for the first term?
Just
So
deduct them.
so the value at the position, let me call this as a C, you know, which is the matrix Cij. Okay. The value of at Cij, you know, comes from the row I of matrix A, row I matrix A, and multiply with the column J of matrix B. Okay. Row I say Ix, and then column B is Xj. Okay. So here, because so we have a C11, C12, C13, or C21, and C22. Okay. So the first term here is C11. It comes from the row 1 multiplied with column 1 of B. Okay. So in this case, you multiply each element in row 1 with the column 1 of B and sum together. Okay. So what do I get here, Tanat?
57.
Say again?
57.
Say again?
57.
57, yes, which is 5 multiplied with 10 plus 7 multiplied with 1, right? So you get 57, okay? How about the next one?
59.
Okay, the next one is C1, 2. So we multiply the row number 1 with the column number 2. So you get 45 plus 14, right? Which is, you say 59. Okay. Next, next one. Okay, please do it again. Almost done. So next one is C2, 3. I'm sorry, C2, 1. So we multiply row 2 with the column 1. Okay. So what do we get?
63.
Yeah, 63, right? And lastly. Okay, please.
66.
Okay, 66. Okay. So similarly, we can do multiplication for B multiplied by A and, well, you know who I'm going to call, right? I haven't called Tiravit, right? Okay. Is that right? So I write down 10, 9, 1, 2, okay, and multiply with A. So I get 5, 7, 6, 3. Okay. So what's the first number that I get? Tiravit. Oh, by the way, three of you
100.
have the name starting with the same alphabet, which is T, right?
104.
Okay. This is the 104. Okay. Next one.
97.
97. Okay, that's right. Okay.
17.
17 and okay. Well, say again.
13.
13. Okay. So I mean, from here you can see, that it's very obvious that multiplication of matrices is not commutative. Okay. Not commutation. No, it's commutative. They're not commutative. No. Let me put underline here so that we see. Okay. Next, let's look at another property that is very similar to previously. We said that A multiplied with B is not equal to B multiplied with A. Okay. I have a question then. So is there any exception for this? Any exception, you think? Can A multiply with B be equal to B multiplied with A, you think?
If elements of the matrix are the same.
Say again. Oh, okay, that's case 1. True. If A multiply with A, well, I don't know whether it's counted because both of them are the same. So, there's no commutative in here.
Oh, sorry.
Another case maybe
Uh,
Tanason or Tiravit. Any
If
other cases?
if A or B are identity matrix.
That's true. If A or B is equal to identity matrix, yeah, that's true. That's true. Okay, that's true. Okay, first one, I don't know whether it's counted, but it's very interesting. Okay, the way you say it. Okay. Next property that I want to give a quick review is related. This is called distributive law. Distributive, no? In Thai, I think it's the การกระจาย, right? Distributive. Okay. So if you have matrix A multiplied with matrix B plus C, what we will get is we can multiply and then plus. Okay. So you notice that for matrix operation, it goes by order from left to right. And when we have multiplication or we have summation, these two are linear operation. So you can just do it like the linear, method. Okay. Next one is called inverse or inversion. Okay. So for inverse, if I have A multiplied with B and I want to find the inverse, what do I get? Okay. If you remember, we get B inverse multiplied with A inverse. Okay. Similarly, we can have a transpose of multiplication of matrix, right? Let's say A multiplied with B, and then we do a transpose. Then we get B transpose multiplied with A transpose. Okay. Okay. For the inverse, we also have another property that whenever A multiply with B, if it's equal to I or identity matrix, then which is equal to B multiplied with A, then in this case we will say that A is an inverse of B, okay, or vice versa. Thanat, Thirawit, and Thanat Son. Do you know what vice versa is? I know maybe I don't write it well. VICE, vice versa. You know what this means? Maybe you've seen it. Vice versa. Mm. Yes or no?
No.
No?
No,
Okay.
no.
In Thai, it means if we say A is an inverse of B, you can also say that B is an inverse of A. Okay. So vice versa in English, it means you can switch this order A and B. You can switch the way you say it. Or in Thai, it means มันก็คือหมายความว่าสลับกันก็ยังถูกเหมือนเดิมอะไรอย่างเงี้ยเข้าใจปะ vice โหดนิดนึงเนาะคำนี้ vice versa โอเค Okay, let me see. Okay. Okay. Also, when you have should I go on this? Okay. Let's look at an example. So this is our interesting way of looking at it. If I have matrix A as 1, 1, 0, 0, okay, and I have matrix B as some numbers like B11, B12, B21, and B22, okay. If the multiplication between A and B, you get the identity matrix, which is 1, 0, and 0, 1. Okay. So let's say this is the matrix C. Okay. So let's say the question is what is the condition for B? Okay. What's the condition for B? Which means that what are the values of B11, B12, B21, and B22? What can they be or what they cannot be? Okay. So if I write this C as C11, C12, C21, and then C22, okay. From previously, we said that C11 actually comes from the first row of A multiplied with the first column of B, right? And here, if you look up here, you see that C11 is 1, okay? And in order to get 1, if we multiply A and B, we multiply row 1 of A and then column 1 of B, you get 1 multiply B11 plus the 0, okay? Multiply with B21, which is B11, okay? If we do it similarly for C12, C12 from here, C12 is 0. We can write that C12 is row 1 multiplied with column 2. Okay. Row 1 multiplied with column 2, element by element. Okay. So here we get B1, 2. Then next one is C21. Similarly, C21, here we have number of 0. Okay. And so when we multiply from row 2 of A with the column 1 of B. Okay, so we get 1 multiplied with B11 plus 0 multiplied with B21, which is B11. Okay, and lastly, for C22, okay, you can do it like similarly, which is equal to 1, and it comes from row 2 multiplied by column 2 of B, okay, which is B12. Okay. Okay. So from here, it means that, okay, from these results, what is, well, I mean, if A multiply with B and you get an identity, we know that B is an inverse of A, right? Is that true? Okay. And the question is, what's the condition for B? What can be B? What can be matrix? Are there many infinite possibility for B, or there's only one value for B? B means B matrix. That you can generate, right? Let me do with this side. I have more space here. So from these 4 lines, you notice that this B, from the result, we'll get that B11 has to be 1. Okay. B12 has to be 0. Okay. And what are the remaining element in B? What do you think? What do you think? Thanatsson, what do you think about the values of B here? That can be inverse of A. No idea? How about
No idea.
how about Thirawit? Thirawit, I know you have ideas. Here we have the values for B11 and B12, right? From these 4 equations, right? Oh, sorry, something is wrong. C12 is equal to B12, C21. Okay, okay, let me use red colors. So the first line, it says that B11 is 1, okay? And B11 is 2, also 0, okay? B12 and B12 also has 2 possibility, right? Okay. Yeah. So B, what can be, what can this matrix be, B? Let's say I choose one case where B11 is this case is equal to 1, and B12 this case is equal to 0. Okay. Because this 4 equation doesn't say anything about B21 and B22. So let's say
It can be 1 or 0.
yeah. So actually what this says is that if let's say that matrix B in this case is 1, 0, and then XX, which is just one case from this equation. Okay. Actually, this equation says that it gives you the conflicting ideas about the values of B11 here and B11 here. Also conflicting values for B12 here and B12 here. Actually, you know what it says in this case? You know what it says in this case? Can you guess? B does not exist. That's what it says, okay? It means that you don't have an inverse in this case. If A is like this, you have no inverse, okay? You cannot find it, okay? We can test it, no? Just for fun, okay? So let me take a look. I have MATLAB open, okay? So let's take a look. For fun, what do we get? Okay, if I let A is equal to 1, 1, 0, and then comma, right? Take a look at this page. Okay, so in MATLAB, you can say 1, 0, and then 1, 0, okay? So you get A like this, okay? And then for B, what can we do? We just say inverse of A, okay? It's one way, okay? If you don't know, you can use help in MATLAB. You can use Python or any other software, okay? But I just want to do it quick here. If you know what inverse means, you can just help INV in MATLAB, okay? Then it will give you like a description like this, matrix inverse, okay? And then it says that they will give you a warning message, you know, if the value you put in here that you want to find inverse is badly scaled or is nearly singular. Okay, badly scaled, I don't know what it is, but nearly singular mean if the determinant is near 0, it may have some problem with it. Okay, so if I do inverse of A, what do I get? Okay, so it means you cannot find it. Okay? But if I do something else just for fun, okay, you can use this method, you know, on the screen, on the slides as a way to find the inverse, you know, just a very simple approach, okay? Because if I switch to the slides here, okay, you see that, so for any 2 by 2 matrices, or even more than this, you want to find the inverse, B11, B12, B21, and B22, you can use this type of equation, you know, just to find the values of each element, okay? And generally, you'll be able to find it, except in this case where there's no specific answer, okay? So let me try something else on MATLAB just for fun. Maybe Thanat, can you give me another matrix of A? Let's do 2 by 2, no? Just for simplicity. Can you give me maybe some numbers?
1, 2, 3, 4.
1, 2, 3, 4. Okay. Okay, this one, it should have a inverse. Okay, so I just do inverse of A. So this is what I get. Okay. So, oh, I should put it as a B, you know, just for the same as this case, A multiplied with B. So I put A multiplied with B. What do I get? What do you think we'll get in this case?
Identity matrix.
Are you sure? Are you sure we get identity? We get, do we get integer number, or we get real numbers, or what do we get? What do you think? Okay, I just enter. Okay, so actually we get something like this. It means that because of some floating resolution, you know, you don't get integer, you get this resolution. Okay. And okay, what else? Let me go next. Okay, let's go to next page. Okay. Oh, it's already 5:44. Okay, we have time, no? And okay, let's look at the next slides, next page. Okay, so there's also another property that you probably have seen it. Okay. By the way, this is mathematics class, So sometimes I prove, some property or some theorem, just out of curiosity. And also when you do research, it gives you a stronger, how do you call it, a stronger background, if you can prove mathematically once in a while, okay? Next property that we will prove, this one, maybe you have seen it. If I do a transpose of the A inverse, okay, what do I get? Okay. I guess you can, if you've seen it, you can guess that you can exchange between this operation, for inverse or transpose. Okay. So let's prove it. Okay, see how it comes about. So how am I going to prove it? So what I'm going to do is first I'm going to start from this property that an identity matrix, if you transpose, you get itself. Okay. Like for example, if you have identity matrix is equal to 1, 0, 0, 1. If you do a transpose, you get 1, 0, 0, 1. Okay, so that means these two are equal. Okay, and then if okay, let me do this. Given a matrix A and let A inverse, which is an inverse of A, exists. Okay, so it means that A multiplied with A inverse equal to I. Okay, if the A inverse does not exist, you cannot prove this. Okay, so therefore, okay, so from the first line here, I'm gonna write I transpose as A multiply with A inverse, and then I do transpose. Okay, and this will be equal to identity. Okay, depending on the dimension of matrix A. Okay, and so I use some property that we had earlier that if you transpose something, you have to transpose each matrix, but then you switch the order. Okay, so here I'll get A inverse and then transpose, multiply with A and then transpose, and then it's equal to A. Okay, so from here you can say that A inverse transpose is equal to A transpose inverse. Okay. Okay. So this is only one-sided proof. Okay. You can do a similar proof, but you you put A inverse multiply with A. Okay. In I instead, so you change this side, you change this thing is okay. For the other side, you get you put A inverse multiply with A instead. Okay, and then you will get a similar result but in switch order. Okay, and then we can say that this is the proof. Okay, so sometimes we use the proof like this to check. Okay. Okay, next, let's look at another additional special matrix. Okay, so today's lecture is very basic, but we'll look at some different special matrix that will be useful later. Okay. Okay. Next one, this one is called permutation matrix. Okay. So this is a special matrix more. Okay. So next, let's look at permutation matrix. Permutation matrix. Okay. Okay. Theoravit, do you know what permutation is? Okay.
ความน่าจะเป็น
No. Permutation means we switch order. We can switch order. It's a matrix. It's a special matrix that if you multiply another matrix, they switch order on the, how do you call it? If you multiply it with another vectors, for example, you know the numbers in the vectors they switch, they rotate. You know, so basically it's a matrix that okay, when multiply p with another vector, okay, basically you switch order of elements in A, which is A, how do you call it? This will be a vector. Okay. You switch the order A because it's okay, AI1. Okay, because only one column. No. Okay. And what are the characteristic of permutation matrix? We'll give an example after this. Okay. So in permutation matrix, each row, okay, or each column, actually or and each row and each column, okay, has only one, okay. The number one, the element 1 exists on each row or and each column only once, okay. And secondly, the permutation matrix is a square matrix, okay. For example, if we look at permutation matrix P4, okay, and I can write it as, let's say, just for fun, no, 1 0 0 0, okay, 0 0 0 1, 0 1 0, 0 0 1 0, okay. This is called permutation matrix. It has a property as listed above. And for example, is a square matrix, okay, with a dimension of 4 by 4, okay. And then for each row and each column, let me change to red color. Each row or each column, well, I should say each row and each column, no? Each row and each column, there exists only one, okay? Number 1 just one time, okay? ก็คือมีเลข1ครั้งเดียว okay? Exists only one. Okay, and what do you mean by what do I mean by permutation matrix that I asked earlier? Let's say that I multiply P4 with another vector, okay? Let's say I put just for simplicity 1 2 3 4, okay? And let's see what happens when we multiply this vector A with the permutation matrix, okay? So what do we get? We get 1 0 0 0 0 0 0 1 0 1 0 0 0 0 1 0, okay? And we multiply with the 1 2 3 and 4, okay? So what do we get? Who hasn't I called this time? Pure, okay.
Yes.
Okay. First of all, here we have the dimension of 4 by 4, right? And this
Yes.
is 4 by 1. So the result will have the dimension of what?
4 by 1.
4 by 1. Okay. So what are the values in here? Let me change.
1.
So
Sorry.
you get 1, right?
Yes.
Okay. First
4.
element comes from the row number 1, multiply with the column 1.
Column number 1. Yes.
Yes. How about second element?
4. 4.
4, right?
Yes.
How about the third
2.
row?
2.
And the
And
last
3.
row and 3.
3.
Yeah, voila. Okay, voila. Okay, so we switch order. Okay, so that's how we do it. Okay. Another property that is the important about the permutation matrix is this. For permutation matrix, there's one interesting property. There are two interesting property actually. One is P transpose multiply with P, you always get identity. Okay. Okay. And for example, here in this case, if you multiply P transpose with P, okay, so P I just write down from the top 1 0 0 0 0 0 1 0 1 0 0 0 0 1 0. Okay, and what is a transpose? I haven't talked about this too much. Who haven't I called? Tirawit, right? Tirawit. What is a P transpose? This is P, right? Tirawit, are you there?
Yes.
Okay, what is P transpose?
1 0 0
Okay.
0.
For P transpose, what we do is we convert each row into column, right? So
Yes.
row number 1, we convert it into column number
Column
1.
1
So we get 1 0 0 0 and then
0 0 0 1
0 0 1
0 1 0 0
0 1 0 0 and lastly
0 0 1 0.
0010. Okay. So now the hard part. Thanat, okay, I know you're quick.
Yes.
I guess you can guess, right?
Yes.
Is something wrong here? Is something wrong? So this transport, did I write everything correct? So this is okay, right? Not, I
Yes, it's
didn't
correct.
write. Okay, so what do you get for P transpose multiply with P? About what do you get?
Of course, you get identity.
Yes, you get, yeah. Now you're too lazy to multiply for me. Okay, so you get identity. Okay, so second property, which is derived from the first property. So what is P inverse? Can you guess what is P, what is the P inverse?
P transpose.
Exactly, right? Because the anything that multiply with P and you get identity, and in this case, it actually will be equal to P multiplied with P transpose. If you don't believe, you can try it out in the example, It means that P inverse is just a P transpose. Okay? So this is a special property of this type of matrix. Okay? So if someone asks you, which matrix has the inverse as its own transpose, you can say what? What do you say? Which matrix has an inverse as its transpose? You can say it's the permutation matrix, right? Okay. Okay. Second one, that's the one of the first special matrix that we looked at for this part. Second one is the diagonal matrix. Okay, this will also come up a lot later when we take a look. Okay, so for diagonal matrix, if I write it as a D matrix, okay, this is a matrix with the element Dij, okay, where Dij, okay, in English, when we say where, it's just a technical way, of saying the condition, okay, and in Thai where ภาษาไทยเนี่ยก็หมายถึงว่าโดยที่อะไรเงี้ยเมื่อให้โดยที่เนาะ so that's what it means. It's not มัน it doesn't mean ที่ไหนนะ it doesn't mean like where are you, you know, something like that, but it means in which, whereby, you know, something like that. So diagonal matrix is the matrix where Dij, if any element that number the row index and the column index are not equal, you get 0. So it means if I is not equal to j, you get 0. Okay. And it is also a square matrix. Okay. So in general, we can write a diagonal matrix like this. Okay. For the remaining values, if they are all zeros, sometimes we just write like this. Okay, which means the rest is all zeros. Okay. Okay. For example, you may have like an identity, but a diagonal matrix as a 1 0 0 2 0 0 0 3, you know, something like that. Okay. An example. Okay. Next one is number 3. Okay, this is easy. Number 3, we define a lower triangular matrix. Okay, let's call it matrix L. Okay, it is also a square matrix. Okay, in which, or you can say whereby, you know, same thing. Whereby. Matrix L, which has the element Lij, okay, and Lij is equal to 0 if the column number is greater than the row number. Okay. And what does it mean exactly? It means, for example, if I look at L lower triangular matrix with dimension of 3 by 3, okay. Here I write as L11, L12, and L13, L21, L22, and L23, L31, L32, and L33. Okay, so it's just a square matrix. Okay, and which elements have j is greater than I? Can you tell? Pure. Which element has the column index larger than row index? If you take a look here, 1 1, right? This is I is 1, j is 1, I is 2, j is 1, I is 3, j is 1. Okay, so in this case, you will find that for these two, okay, j is less than I, right? Or I is greater than j, okay? So which one has the j greater than I, pure? Oh, nope, you disappear again, okay.
L12,
Okay, L12,
L13,
L13, and
L23.
L23. Yep, yes. So these values, you know, in this these values above the diagonal line, okay,
Yes.
these values or elements, okay, above the diagonal line, okay, from the definition is all equal to 0, okay. So this is what we call lower triangular matrix. It's a square matrix where any values above the diagonal line is all 0, okay. For example, I can have L33 equals to, let's say it's 100, okay, 10, 13, 0, 25, minus 1, 0, okay. Is this considered a lower triangular matrix? Tirawit?
Yes.
No, no.
Well, we need to take a look at the values above the diagonal line. This is the diagonal line, right? Are these values all zeros? Okay, so if they are all zeros, then we say that it is a lower triangular matrix. Okay, so we only consider the values above the diagonal line. Other places is okay. They can be whatever. Even the diagonal
Okay.
line, you can have, let's say I change to 100, 10, 0, 0, 25, minus 1, 0, Is this the lower triangular matrix? This one?
Yes.
Yes, it's lower triangular matrix. Yes. Okay, so it's yes in this case. Okay, so I mean you can guess that similarly we can define a similar triangular matrix, but we change to upper triangular matrix. Okay, and normally in this case we write it as a U. Okay, and you see later why do we do this? Because after this we will start to decompose matrix into smaller chunks, and there are different ways of trying to decompose these big matrix into different chunks, and one of which is to convert a matrix into lower triangular matrix multiplied with the upper triangular matrix. Okay, so you can define similarly for an upper triangular matrix, but let's call it U, no? Like upper. Low L is like lower, and then U is like upper. Okay. So for upper triangular matrix, the definition will be slightly different. Okay. Oh, let me write it, no, so that it's more formal. Okay. But you can define it similarly. Okay. So number 4, an upper triangular matrix. Sorry, upper triangular matrix. Sometimes my hands go quicker than. Okay, upper triangular matrix U. Okay. Okay. Also is a square matrix. Okay. And okay, given that U is equal to Uij, okay, then Uij is equal to 0 if j less than I. Okay, so very similar definition. For example, if I look at U of size 3 by 3, right? Then I have U11, U12, U13, U21, U22, U33. Oh, sorry, U23, U31, U32, and U33. Okay. Okay. So in this case, Who hasn't I asked yet? Let's see. Well, what are the values for uij where j is less than I, meaning that the column index is less than the row index. Okay. So this is the diagonal line. Okay. For this diagonal line, I is equal to j. Above this, we saw it already that I is less than j, right? So you can guess that for I is greater than j or j is less than L is here. Okay. So in this triangle, okay, it's all 0. Okay, that's all. And for example, just for fun, you can say this is 2, 3, 0, 0, 1, 2, 0, 0, 1. Okay. Is this an upper triangular matrix? Tanat, is it an upper triangular matrix?
Yes.
Yes. Okay. How about a null matrix? How about a null matrix, which is all 0? What is it? Is it a lower triangular matrix or an upper triangular matrix?
Both.
Or identity? Identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Are these two considered lower triangular matrix or upper triangular matrix? Tirawit? Any comments? Any idea? No.
It
Well,
both.
yes, yeah, exactly. Because both of these matrices, they fit the definition of both lower and upper triangular matrix. Okay, so these two matrices, they are considered either upper triangular matrix or lower triangular matrix. Okay. Okay. Next, almost lastly, what time is it now? I'll finish a bit quick today. No, not so long today. It's the first time. Next time it's going to be more intense. Okay, let's look at one property. Okay, one property of this lower triangular matrix and upper triangular matrix. Okay. So one of the important property we'll use later next class is the product of two lower triangular. I just write it as triangle. Okay, lower triangular matrix. Okay, is also a lower triangular matrix. Okay. Oh, I need to say two matrices, right? It's also a lower triangular matrix. Okay. And maybe I don't need to prove this part, but we can give an example. Okay. Let's say, okay. Okay, Tanatson, can you give me a lower triangular matrix? Let's say 2 by 2, just for simplicity.
sorry ผมลืมเปิดไมค์ครับเมื่อกี้
No problem, no problem, no
โอเค
problem.
ครับ
Yeah, can you give me an example of a lower triangular matrix? Let's say it's a 2
one
by 2 is fine. Okay,
โอเค
so it's
one
1, yes,
0
0,
2
2,
3
3. Okay, so how about pure? Can you give me another lower triangular matrix? Let's do it a 2 by 2 as well.
3
A 3,
0
0,
3
3,
5
5. Okay, so none of you like negative number, no?
Yes.
You like positive numbers only. It's fine. And so let us multiply, no? So what do we get here? So you see that in this one is a lower triangular matrix. This is a lower triangular matrix. Let me call it as L1 and L2, right? Just to show it. So when you multiply, you get L3, hopefully. Okay. So what do we get? So the first element, we compute from row number one multiply with column number one. So element by element, no? So what do we get?
3.
Okay, 3. How about next one?
0.
0. Okay.
15.
15. And finally,
15.
15. Okay. So is this a lower triangular matrix?
Yes.
Okay. Okay. So we can also define another property similarly. Let me write in red color. No, I'm not going to write the property again. Okay. Should I? Okay. Let me just write it. Otherwise, it's too messy. Okay. Another property similarly, but I'm not going to give example now. No. Similarly, the product you can guess, no? The product of two upper triangular matrices, okay, is also an upper triangular matrix. Okay, I think you can guess, but there's no need to. I'm not going to give example here, okay, because you can sort of guess. Okay. Okay. And also, what are other important property? What are so important about this lower triangular matrix or upper triangular matrix? Okay. So more property. Okay. Maybe I'll give you example. To give example later. Okay. If L is lower triangular matrix, okay, then L1 exists. You know what exists mean? You know, right? And similarly, if U is an upper triangular matrix, then U inverse exists. Okay. Okay. For example, we can look at an example just for fun. Okay. Okay. Example. Okay. If I give a lower triangular matrix as this one. Okay. Who hasn't given me some numbers? Tirawit, right? Tirawit. Okay. Let me do it this way. Okay. So previously we already have some lower triangular matrix number. No. Let me just write it down. So 1, 0, 2, 3. Okay. So I want to ask if I multiply L with L inverse, which is equal to 1001. Can you work on this and tells me what is L inverse? Okay, to start with this, we'll do this 1, 0, 2, 3, and multiplied with, let me call L11, L12, L21, and L22. This is equal to 1001. Okay. So what is L1 inverse? Can you work on this? I give you like 3 to 5 minutes, okay? And I'll come and ask you again. Okay, I'll give you like 3 to 5 minutes, no? I'll come back. Okay, let me ask what each of you get for the answer. Okay, you don't need to get the same solution. Okay. Okay, let me ask one at a time. Okay, say, Tanat, what do you get for? Let me put in red color. Okay, if you don't mind. Tanat, what do you get for L inverse? No need to get the same solution. Okay, if there are many inverse, it's okay.
I got 1, 0
You get 1, 0,
minus 3 divided by 3. Minus 2 divided by 3.
minus 2 or 2/3, right? Minus 2/3, and
And
then
1/3.
1/3. Okay, how about Thanat Son?
I got same him.
Oh, same thing.
Yes.
Okay, you get the same thing. How about Thirawit? Uh-huh.
Same.
You get the same thing. Oh,
Yeah.
how nice. How about Pio? Pio.
Same too.
Okay, so I guess in this case, there's only one inverse, right? Right, and you see
Yes.
that in this case, the inverse, as the stated by all of you, and inverse, in this case is 1, 0 minus 2/3, 1/3. Okay, it is also a lower triangular matrix. Okay. Okay. So if there are many inverse, then you will get different results. Each one, you don't need to get the same thing. Okay. And in this case, I'm just questioning. So okay, I believe you. Okay. And so okay, let me conclude this lecture with this. So why do we look at all these special property? Well, one of the things that we will see next time is, let me change color again. One of the property or things that we will see next time is, if we are given a matrix A, okay, uh, with the dimension m by n, okay, we can write it as L times U. We can decompose it. We can also decompose it into LD and also W, which is also upper triangular matrix, but we pull out some values in the diagonal matrix here, okay? And once we are able to do this, when we compute the inverse, we will get W inverse, diagonal inverse, and also L inverse, okay? And it will be very useful, and it will give us, many other interesting property, okay? Later on, for use. And as you know that the diagonal matrix is very easy to find the inverse, right? And then for lower triangular matrix and an upper triangular matrix, we will be able to find this value very easy, okay? So that's one way. So during the next lectures, we will see a lot of decomposition of a matrix. We can decompose into various components, and then from there we can utilize a lot of properties involved, okay? So let me conclude today's lecture like this. And for homework, generally I guess I'll give you like once every 2 weeks or 3 weeks, around that, and that will be how to go forward, okay? So before I stop the lecture today, does anyone have any question? Also, you can read the textbook. So the textbook will have a lot more details on many properties and all that. Today we are at chapter 1 in the textbook, okay? So any of you have any question? Thanat Son, Pio, Thanat, and Thirawit?
No.
No.
No, not yet.
No.
Okay.
Yes,
Okay.
today is Sunday.
Okay. So I go a bit slow. I went a bit lightly today, no? Okay.
Yes.
Okay. So I guess I'll see you next time on the same next week on the same time. Okay.
Yes.
Yeah.
Okay. 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 Have a good evening. Mhm.
Thank you.
Okay. And if you have any question, you can text me or whatever, very easy to reach. Also, I go to campus twice a week or 3 times a week generally. So you can see me there. Okay. Mhm.
Okay.
Of course, with some social distancing, as always. Okay. Talk to you all later. Okay.
Okay. Thank you.
Okay. Have
Thank
some
you.
rest.
ขอบคุณครับ Ted
ครับ
Thank you
สวัสดีค
ข
รั
อบบ คุณ
สวัสดีครับ
ค
ต
รั
รงไหนไม่ทราบไม่เข้าใจอะไรก็ถามแทรกมาได้เลยเนาะไม่จำเป็นต้องเร็วมากค่อยๆไปอือฮึโอเคครับโอ้อันนี้ Okay, see you, Pio.
Yes. Today, Bash told me how to use the GNSS receiver.
Oh, already?
Yeah, not finished yet.
I see.
That's why I late for the lecture. That's I think one.
Oh, no problem, no problem. You can
Yes.
continue more. Yes.
Okay.
It's a very expensive. That GNSS receiver cost. Oh, let me wait. Let me stop the recording. Okay. Yeah.